This is our 3-story shear tower structure. It's a multi-degree of freedom system with 3 masses, 1, 2 and 3, all connected together via spring elements, 4 spring elements from the base here to the first mass, another 4 spring elements between the first and the second masses, and the second and the third masses. So each of these masses can essentially move independently from one another, and we have it excited through a base motion scenario here, where we have a motor here rotating, driving a worm drive gear system here with an eccentric drive in here, similar to the single degree of freedom Cousins rig that we have also included in this series of videos. Here is a displacement transducer, which is in this case an LVDT, and that measures the frame displacement. Here you can see we had also some brackets mounted which we can connect similar displacement transducers to measure the displacements of each of these individual masses if we wished. But for the sake of this demo, we're really just showing how this system can be used to understand the nature of the dynamics of 3 degree of freedom systems, lumped mass systems. You'll have noticed I just reached over there and turned on this power button for our motor speed controller. We have a frame speed rotary potentiometer here, and there's also another rotational potentiometer here through which we could also control a damper if we also had a damping mechanism included. Here you should hopefully be able to see that this eccentric motor is driving the frame backwards and forwards with a specific deformation or deflection. I can adjust the frame speed with this potentiometer controller here and drive this at a frequency of my choosing. And I have nice fine control of the frame speed. And I know that from previously setting this up that the first natural frequency of this system, where all 3 masses move with a large displacement amplitude in phase with one another, is at 0.95 hertz. So I'm approximately at 0.95 hertz here. We can get quite close, and you can actually see as I change the frequency slightly until we reach steady state again, which takes some time for us to reach steady state. Now we can see a very nice high amplitude of vibration. That's the first mode of vibration. So this is the particular solution from our solution to our equations of motion that we are observing in action here. If I increase the frequency to the next known resonant frequency for this system, of course there are 3 degrees of freedom, so there are 3 natural frequencies. You will notice that this starts to get a little bit louder the higher in frequency I go. You might also notice that the noise is coming about as a result of perhaps some resonant frequencies from some structures around here that we're driving at this natural frequency. So I'm just going to help the system reach steady state by stopping the motion of all of those masses which are still vibrating as a result of previously driving the first resonant frequency. Here you can now see very nicely a characteristic second natural frequency for this kind of a 3-story structure at 3 hertz. In this case, the 2 masses 1 and 3, are moving out of phase with respect to one another, whereas the second mass here is essentially stationary. You'll notice there is a little bit of vertical displacement as a result of the fact that these spring elements, which we assume to be linear and in our models, are of a fixed length, and so of course there is some rotation. This is quite a lot of amplitude of motion, so small angle approximations may not any longer hold, for example. These sorts of things that we use to linearize the models that we use to model these types of systems. We take small angle approximations and so on, those are not necessarily always relevant, but as we've said many times, all models are wrong, some are useful, and we can model these kinds of systems and get results that are very close to the ones that we observe experimentally. That's the second resonant frequency at 3 Hz. I increase the frame speed again to 4.6 Hz. Now you can hear the motor working quite hard to achieve this natural frequency, or this excitation frequency, I should say. I will stop the tower and allow it to start from a steady state. x0 equals 0. Velocity at time t equals 0 is also 0, and in this case a little bit too high on the frame speed here. Just reduce that slightly. We'll hopefully see the third mode of vibration very clearly, where these mass 1 and mass 3 are essentially stationary, and mass 2 moves independently of those two masses. You'll notice that for each of these 3 different degrees of freedom, the amount of displacement that we observe in each case is becoming progressively smaller. There's a lot more energy in here, but the displacement that is what we observe at higher frequencies is lower for a given velocity and acceleration. So as well as looking at displacement when we're dealing with vibrating systems, we must also think in velocity and acceleration terms. And the acceleration of this second mass could be the same or more than the acceleration of the other masses in the other scenarios, in the other modes, purely because of the fact that the frequency is higher. So we have to think about the differences between x dot and x double dot in terms of, you know, those as a function of frequency. They're all a function of frequency as well. That concludes this demo on our 3 degree of freedom multi-story tower.